Good morning. So today let's study about I2C Communication Protocol. So I2C is a famous communication protocol used in most of the microcontrollers, microprocessors, peripherals. So it's named as I2C, that is inter IC communication. It's called as inter IC. So I square C, some people will call it as I2C. So these are the naming conventions. So at first, the I2C is actually designed by Philips in the year 1980s, and it allows actually easy communication between the two devices. The only advantage of I2C is it carries, it's a serial protocol and uses only two IO lines for the communication, and it is it's a kind of synchronous communication. So later, the I2C, the Philips semiconductors migrated to NXP in 2006, and now also you can find most of the device or the sensors comes with I2C communication. So in general, I2C means inter IC. It is meant to communicate between two different device on a board. Okay, it is not for a long range communication. It is on a board, on a PCB. If there are two devices kept, so instead of communicating with the other device parallelly, you can communicate serially. So as you can see here, you have actually a slave device and a master device. Usually master device is one which controls all the slaves, and it has an I2C bus, which is conventionally known as SDA and SCL, and they are tied up together between these two lines. So SDA will be communicated with the SD of the SC slave device, and SCL, that is a clock, is given to the slave device. So we need to extract information between the master and slave. So let's look more about this, how exactly this communicates. So as you can see, the features of the I2C communication. So I2C features are, the main feature is it uses only two IO lines. That's the main features, that you can connect, n number of devices, but there is a restriction for connecting number of devices. I'll tell you how, what is the number of devices, but I can connect more number of devices. So there is an addressing protocol used to decide the number of devices to be connected. And the another thing is, each slave device is identified by an address. So when you connect any device, so you need to assign certain address. Usually that addressing is done with the 7-bit address. So that is something universally adopted system. Whenever you find a device I2C, first thing is to know about what is the address of the I2C device. So if you have an I2C device, then there should be a 7-bit address. So as you know, if there is a 7-bit address field, then you can have a combination of uh, 127, 0 to 127, that is all I. So totally you can connect up to 128 devices. So we can have 128 devices parallelly connected on an I2C bus, and always it is labeled as master and slave. So as you know, the connection, see this connection, if you see the master and slave, so the slave device will have an address which is internally written, and in some cases the address is fixed. Okay, some cases we have a dynamic allocation of an address, some cases it is static allocation, because the thing is already programmed, the IC will be already programmed with a certain address. So we can actually change a few bits of the address. So if you want to connect multiple sensors or multiple devices the same type. So uh, another thing is, all the transmissions are initiated and terminated at the master. So the master is a main device which takes control over all the slaves. You cannot communicate between, two slaves cannot communicate with each other. So it has, the communication has to be through the master. Okay, that's one thing. And the next thing is the physical bus. If you see how exactly the I2C is connected. So whenever you look into an I2C bus, you will find the two lines, that is SDA and SCL lines, as you can see here. So this is actually the SDA, which is a data line, and SCL is a clock. So together is called as I2C bus. So when I say I2C bus, it means that there are two lines in it, and you can see there is a resistor connected. Usually this resistance you need to connect, it depends on the type of the connection. If you have many devices, the sourcing current required, actually for that purpose they are given it as a pull-up resistor here. So usually this is pulled to high, logic high, though this connection is actually made to VCC, so that the required current can be acquired from these pull-up resistors. So as you can see, SD is a serial data and serial clock is SCL, and the SDA carries the data required and SCL carries the clock. So it is synchronously, the clock will synchronously go along with the data. There are certain rule that we need to go into study, but you see one thing, the devices are connected parallelly. So this is device 1, this is device 2, this is device 3. So I can have now n number of the devices here. So device 1, device 2 and device 3. So they are parallelly connected to the I2C bus. So this will be having one address, device 2 will be having another address. So you cannot find a unique address between these two devices as same. Yeah, you can find a unique address for this, so none of the device will have the same address. So that's one thing you need to remember. So how the devices are addressed? So if you look at this, now see here, the master device is connected with an SDA line and SCL line. So the I2C protocol is such a way that in a board, okay, you can connect sensors, you can connect different actuators, drivers, basically some memory device, some IO device, you can connect many devices. So whenever you have, the number restriction on the IO lines, the maybe you want to decide the board size, so usually they prefer to go for I2C. That is the main purpose, that because you have only two lines for the communication. So even MSP 430 ARM series and even the recent 8051 core, a mini device will have an I2C bus. It has become a somewhat default. The so what they do is, whenever they connect certain device on the addressing, I mean on the board, there is a one thing that you need to remember is the device addressing. So you see here, device addressing, as I mentioned, it is a 7-bit address. So says there is a slave device addressing is 1101.001. So this is one of the, so this addressing is actually this comes around the value 69. So 69 is the address of this slave device 1. There is another device here which addressing is 44CH. Okay, 4C is the slave address, and here it is 2E 27 is that 27 is this slave divided address. Okay, this is 27, this is 4C, and this is 69. Okay, these are different address actually. So whenever you want to communicate, you need to assign certain values here, address. So whenever that address will be received by all these, because eventually when you are sending a data, all the device will get the address, but who will decide which address? The address is decided by this slave, whichever gets a match, so that will respond. So depending on that, the data bus will be open for those devices. Okay, so that's how the addressing is done. So main thing you remember, the slave device addressing, that's one thing that you need to remember. So remember that in I2C, device addressing is 7-bit. That's the first thing that you need to remember, so that you can have up to 128 devices. So you can connect as many devices you want. Okay, and this using SDA and SCL line. Now let's come to the next. What is the data transfer protocol? So when I talk about a protocol, protocol is a rule, the rule with which the device communicates. That's one thing you need to understand. So maybe it is a little bit complicated to discuss about the protocol, but we can make out some of the highlights about these rules. In I2C bus, there are some standard signaling. They are called start condition, they are called as stop condition, read write bit, and acknowledgement bit. These are some of the standard naming that we use in the I2C bus. As you can see one picture here, okay, which represents the the protocol. So there is a start condition that will come, that generated by the signals. We will see what is how that start signal is generated. Once the start condition is achieved, the immediately after start condition, the data bus, the SDA line, will provide you the 7-bit address. So that contains the slave device address to be communicated. So whichever the slave device you want to communicate, that device address you want to put. For example, here if you see, I have a slave device address which address is 69. If I want to communicate from this master to the slave, what I will do is I'm going to send first address of the device. So I need to address. So it is as good as calling your name by a register number. So I need to have a unique identification. So here what they do is, after developing a start condition, soon after the start condition, they will put the address serially. They will put, so 69H will travel here because I want to communicate with this slave device. So once you do that, next, as soon as there is a resemblance, okay, there is a match, because this slave device now has to respond. So once you give a start condition, all these devices are active and it will be reading the data bus. Once it will read the data bus for the address sequence, whoever the device gets a match, that will respond. How it will respond? You see, there is a acknowledgement bit. Now before that, you need to decide what you want to do with the device, whether you want to perform a read operation or a write operation. See, I can have an I2D device, maybe let's say a temperature sensor I have. So temperature sensor usually gives me the reading, okay. I can even actually write some configuration bit. Also I can do some temperature read operation. So read write both possible with any of the device. So generally these I2C device are not a single register, it has a multiple registers in it, and each device, each registers will have a particular address actually. So what they basically do is, whenever you are actually configuring certain device, after start condition, along with the 7-bit, one more bit will go, that will go as a read or write bit. Usually read bit will be 1 and write bit will be 0. For that you need to decide, you need to see the particular data sheet, okay, whether it depends, okay. Usually read will be 1, write will be 0. We say write bar and read. So once you send that information, now the device will respond here. So for example, you want to read the slave device, okay, then you will send start condition and you will send the 7-bit address, that is 69, and then you will send the read bit, that you want to read the device. Then immediately this acknowledgement, okay, the white color and there is a the blue colored highlights are given. So these are all something slave is master is sending, and this will be respond, okay. This is the response of the slave device that gives an acknowledgement bit, that saying that that device is present and it is ready to do the operation. That is actually given as another bit in the timings diagram, okay. So in a particular timing sequence, this will also will come from the slave, indicating that the device is ready. Once the device is ready, the next operation is accordingly whatever we have asked. Whether we are performing a read means you will get the next 8-bit data ready for the either it is, if you want to write the data, maybe if it is write, then it will be 8-bit data from the master. If it is read, if it is in, this will be an 8-bit data from the slave, and you will get an acknowledgement bit also from the master or the slave, depending on the successful reception. And then you get a stop condition. So if you look at this overall protocol, what you can see is all these datas are serially put up in order. First thing is a start condition, next is a address condition, then you have a read or write condition, then you have an acknowledgement bit, then you have a read or write data to be put to the slave device or from the slave device, then you have an acknowledgement bit, and finally a stop condition. So the main thing that you need to see here is these are the conditions. So an I2C protocol will, whenever you're performing some data transfer, remember that there is a start condition, there is a stop condition, there is a read write bit, there is an acknowledgement bit, and each one of these will have its own functionality as I mentioned. So let's look at in detail what is actually the start condition. So usually in I2C, start condition is referred in this way. Whenever the SDA goes from high to low, okay, the SDA line goes from high to low, if the SCL is remains at the high period, then that is a start condition. Okay, this condition, the SCL should be at high, SDA goes from high to low. This is a start condition. Whereas SDA SCL is at high, whereas SDA goes from low to high, then it is a stop condition. So this is how we discriminate between start and the stop condition. Now you get an idea how the start and stop conditions are achieved. So rest all actually sequencing the data. You are slicing the data as per the number of bits that you want to get. First thing is to achieve how these start condition and stop. This is very important in I2C, and usually these start and stop conditions are generated by the controller itself. We did not go for generating a start bit and a stop bit by writing a separate coding for that. So whenever there is a chip that has an I2C protocol, you simply have to write the register, and the register, when you write some configuration bits, the communication starts by itself by generating the start and stop condition. So in MSP 430 or the ARM, if you see, these are already implemented. Okay, but what we are trying to understand is the communication protocol, how this communication protocol is organized in I2C. Okay, so let's look at the, so this is about the start and stop bit that I have actually explained you. Let's go with some details about how the data will be sent to the slave device. So there is a sequence that we need to learn or understand. What are the procedure? See, if you want to send a data to the slave device, for example, what is the situation that I need to or that we may get when you want to write some data to slave device? For example, you take, there is a memory. Okay, there is a memory device. So when you have a memory device, so you need to write a data. Okay, let's say we want to write some data to the memory. So my memory is an I2C device. It is not a parallel communication, it's actually an I2C device. So usually in a memory I want to write some bit. Take an example of let's take an example of say you are writing an RTC, okay, real time clock. Let's take, so real time clock you are using. So you need to write first the time event, so hours, minutes, seconds, for where you want to start running your clock. So you need to write, you need to transfer the data first to the slave, saying some minutes, hours, second information. So that's actually you are sending information. So it is actually you are writing to the slave device. So what is the procedure involved in that? It is the same protocol that I have actually discussed earlier. There is a start, there is a addressing, there is read write, then there is a data, then there is a stop. So this is a protocol. Let's see, but this protocol may vary slightly depending on the device that we are using. So take an example here. Whenever you are going to send data to the slave device, what and all need to be done? See, the master device sends the start condition that I mentioned you already. It will send a start condition. How the start condition is? Start condition will be something like this. The SDA will be from high to low. That time SCL will be at high state. So that's actually the start condition. So next, after the start condition, next the master device sends the 7 address bit. Okay, it's actually the address bit in I2C is always 7 bit. That you can remember. It's a standard protocol. You cannot change that address. If you try to change it, then there is a incompatibility with the device that we normally use. Universally, this protocol is accepted, and everybody, whenever you're developing some device, they are developing for 7-bit address only. Okay, so the master sends a 7-bit address which corresponds to particular slave device. Since we are writing it to the memory, so every location, okay, is treated as an address, and from that address onwards the data will be read. Okay, so maybe you are writing to a register called maybe address register, maybe it's a hour register, minute register, second register, maybe an RTC. Then you want to address which register you want, so you need to address that. The next is slave address to be targeted. Once it is done, the master device responds actually by setting the read and write bit to 0. So since it is first time that we do is actually a write operation, okay, we are doing a which signifies that I am going to write. So we are sending the data actually to the slave, so it is a write operation. So since the write bar, this bit should be 0. So in the protocol, if you see here in this protocol, this RW bit should be 0. Okay, so that's what the meaning is. The next thing is, now there are two things possible after sending the write. So you have identified, you have signaled the start condition, you addressed, and you have decided that you want to do a write operation to the slave device. Now what response may come? There are two response may come. Either it can acknowledge or it can send no acknowledgement. So the device may be there, it may not be there, device may be damaged, it can be anything, or your addressing may be wrong. So according to that, there are two conditions possible. If no slave device matches with the address, okay, then it will send no acknowledgement. That is obvious. Okay, so this signals the master device that slave device identification is unsuccessful. That's one thing. And master clock will end the current transaction by sending the stop. It will send the stop signal, it will end the transaction. Nothing can be done. Okay, if the slave device exists, then the slave device will respond to the master device by setting the acknowledgement bit to 0. So here acknowledgement bit is signaled as 0. Obviously no acknowledgement is signaled as 1. Okay, then the next set of operation happens. So after that, on successful, let's see what happens. If the slave device is successful, there is a slave device. Now the master device will send the 8-bit data, okay, which is considered as for the slave device, and that means you are writing it to that slave device. Okay, so it will send directly, the next signal is actually 8-bit data, it will send to the slave device, and the data will be put up on the data bus or the SDA line, and in the sequentially the master will send the 8-bit data. Now if the data is successfully received by the slave, again there is an acknowledgement, it will send who sends, the slave will send as a 0, which indicates it is actually successful. In case it is unsuccessful, then it will repeat from the step number. Again it will send the start condition, again the whole process will repeat. Okay, so in this way, so you can keep sending the data continuously. In some case it depends on the next addressing also, you can address in the same way. So consequent memory devices inside the slave device addressing can be done by with the single start condition addressing consecutively. You can keep sending the data, it will write to the different register. If you want to stop in between, send a stop condition. So that is the end of the protocol. Probably this can be clearly understood when you really implement an I2C communication protocol with certain device. Okay, so let's look into the next stage. This is an example of I2C write that I was actually talking. You see here, this is the start bit that we sent, then there is the address bit that is sent, and this is write bar. This 0 indicates the write bar operation, and this is the bit address, okay, device address. Now you may get an acknowledgement bit here. Once you get an acknowledgement bit here, then you get the data bit. So the master will send the data to be written, and again an acknowledgement and stop. So this is how you are writing it to the particular slave device with certain value. The device could be anything. So this is a protocol. Next, you see how you're going to read it. So this is again the same way. uh, what we need to do is, first we need to master device, we need to say that we are going to read. Actually, instead of writing, now I'm going to reading the slave device. Maybe you're connecting a temperature sensor. Let's say you're connected temperature sensor. The temperature sensor has an I2C protocol, so you want to read the temperature from the I2C device. So now the whole scenario, like usually we connect, temperature sensor means a thermistor should be connected, and from the thermistor I need to get the analog value that has to be converted to digital by A to D conversion. All sort of things are need to be done. So the recent trend is not that. So what we do is we use a sensor which has an I2C bus. So it's a system on chip which takes care of all the conversion things, and you get a ready digital format data. So it is the latest trending. Okay, so usually anybody who designs a system, nobody will go now, except in some exceptional case. If there is a requirement of ADC, then only they prefer. Otherwise it's all system on chip now. We get an ASIC device for temperature sensor which has an I2C, which has an SPA protocol. The advantage is you need to communicate with the less number of IO lines. Okay, and you don't have to have an ADC, all that thing. It's all calibrated, so you can get the ready reading and you can actually put it on the display. So that's why they prefer for I2C. That's why the I2C is important. So now why I'm telling this temperature, because a temperature sensor with an I2C is kind of an example where I can explain you the reading from the slave device. So your master is now connected with the temperature sensor. Now the temperature sensor is a slave device. So now you want to read the temperature value from the slave. So how we are going to read it? So first procedure is, first you should know the device address, which is the temperature sensor that you are using. It may be LM75, or it may be there are temperature sensors. Actually, you can search it in the internet. You will find a lot of temperature sensors with I2C protocol. So, and when you refer to the data sheet, you will get the device address. Okay, so the master will send the read, because it is 1 now instead of 0. Earlier we sent 0 for the write. Now I am going to read it. So the target slave device will respond to it, and then the next cycle, master is not sending the data. Now the slave will send the data. Okay, now slave will send 8-bit data along with an acknowledgement bit from the master. So master will respond to the acknowledgement now. So slave first, after sending the address for read operation, slave will send acknowledgement. After sending acknowledgement, immediately slave will repeat sending the data which is required by the master for that address. Now the master will respond to it by sending the acknowledgement bit to the slave. So that completes the operation. So once the required data is received by the master, it sends an acknowledgement bit. Okay, so then the slave device stops sending that and releases the STA bit. Okay, so there should be an acknowledgement. Actually, if the master device to read the specific internal location of the device, so you need to first send that you want to read, then you want to send address, and so on. So you can see this protocol here. Again, there is a detailed protocol. I2C read, when you are doing, you see here, this is the simplest way of understanding the I2C read. There is a start bit, there is a device addressing, then there is a read or write bar. Now it is read since it is 1 here. Then there is an acknowledgement bit, and then the data will be sent, and then there is a no acknowledgement. There is no acknowledgement because it is going to send the data, and there is a stop bit. So this is how it's going to work. So if you see the timing diagram, this will give you the in actual scenario how the communication that happens for the transfer of data. As you can see here, so this is actually the data bus, and it continues here. Actually, you can see the arrow, it starts from here, it goes here, and it ends up here. So every time, this is the SDA line that I'm talking. This is the top one is an SDA, the bottom is actually the clock. So every clock, this is a start condition. You see here, this is a start condition, and soon after start condition you send the 7-bit address information along with the clock reference, and there is a read write bit you send, then you get an acknowledgement bit, either it can be successful or unsuccessful. After that again the data will go either for read or write depending on, and finally there is a stop condition. So this is a brief introduction about I2C. So in summary, what I can summarize here is, now you know that the I2C is a serial protocol with the I2C bus having naming convention SDA and SCL. SDA is used for the data and SCL is used for the clock. Okay, so and the communication protocol has four different stages, starting with the start condition, then the addressing, acknowledgement, read write, and stop. These are some of the signaling in I2C. So what do you mean by start condition? Start condition, it's a start of this protocol. Stop condition is the end of the protocol. So there is a signaling, what you have seen, how the start and stop signals are produced, and the addressing, how the addressing is done. So now you can remember always the I2C protocol will go in a sequence: start, address, read or write, acknowledgement, then data, and stop. So that varies from whether you're going to do a read operation or write operation. So this is about the brief introduction about the I2C, and I2C is a general topic. MSP 430 has an I2C protocol, so which can be accessed by accessing the respective register. So one thing is to understand the protocol, you need to understand. Then if you know the protocol, then any processor you take up, you can actually handle the I2C communications. Okay, so temperature sensor, pressure sensors, then RTCs, memory device, ADC, LCD, there are many devices, even camera modules. Every device nowadays comes with I2C. Okay, so you can handle any device with I2C. If you know I2C protocol very well, you can connect any device to a controller. You can handle any embedded system gadget to work on. Okay, so that's it about the I2C protocol. Thank you.